So what is happening to try to address climate change? That is the topic of our last section here. In 1997, the Kyoto Protocol was put in place. For that protocol, 38 countries met to create binding agreement to reduce greenhouse gas emissions. Means of reducing CO2 emissions, we have make and enforce energy conservation rules, require all new homes to have solar heating, require auto manufacturers to increase fuel efficiency, and raise the minimum driving age to 18 years. Fewer drivers, less CO2. Key findings of the 2000 U.S. Climate Change Assessment, which was mandated by Congress. So, given that CO2 will continue to rise 1% per year, that will result in increased warming of 5 to 10 degrees Fahrenheit by the year 2100. It'll have differing regional impacts. Some will be drier, some will be wetter. We have very vulnerable ecosystems, and those vulnerable ones are going to disappear, including alpine meadows, coral reefs, and barrier islands. There's going to be widespread water concerns. There's going to be more droughts and more floods. Agriculture will be largely unaffected. Not sure exactly how they came up with that. There you go. Forest growth. There will be initial increase due to photosynthesis. The coastlines will be affected due to rising sea levels and increased storm frequency. There is a TED Talk on more recent findings. Again, I will try to remember to put that at the end of the unit. If I forget, remember you can always access the PowerPoint through the resources folder. There's also this issue with the ozone layer. So ozone is a molecule composed of 3 atoms of oxygen. It's produced when diatomic oxygen is bombarded by UV. So here's a schematic of that. The oxygen absorbs short wavelength ultraviolet light at 160 kilometers. Diatomic oxygen absorbs different ultraviolet light, and ozone absorbs long wavelength ultraviolet rays. So you need all 3 of those, and you have the biosphere protected as a result from UV radiation. The ozone layer forms in the portion of the stratosphere which is closer to the sun. And it basically is like a blanket surrounding the Earth which filters out this harmful UV radiation. The hole in the ozone layer began forming in the early 1980s. The amount of ozone is measured in this unit called Dobson units. The bigger the number, the more ozone there is. So we can see in 1981 over Australia we had kind of a pale blue, and by September 1999 it was a dark blue, which in Dobson units means it's gone down. That is our ozone hole. Chlorofluorocarbons, CFCs. They're organic, non-toxic, non-flammable molecules consisting of chlorine, carbon, and fluorine. When hit by radiation, when hit by the UV light that the ozone is supposed to be taking care of, the chlorine breaks off and destroys ozone. So here are a couple of reactions. CFCl3 is our chlorofluorocarbon. Add UV light to it and you end up with one chlorine atom and CFCl2. That one chlorine atom that was just created then interacts with the ozone to create a molecule with Cl and O, chlorine and oxygen, and then leaves a diatomic oxygen. Right. Refrigerators and air conditioners, that's a source of freon. Those are your CFCs. Production of plastic foam also is a way of getting CFCs released. The pressurizing agent in aerosol cans also is a CFC. So how do the CFCs get up to where the ozone is? So down here on the Earth, we have all sorts of fun things happening. We have evaporation and convection, not a big surprise there. We have sulfur being emitted by the oceans. That goes up and comes back down. We have natural and anthropogenic emissions from the Earth, including things like methane, carbon monoxide, carbon dioxide, sulfates, black carbon dust, nitrous oxide. Here's our CF2, any of the other NOxes, and some ozone as well. Those get carried up. At the top of the troposphere, we have ozone production. And the halocarbons and the CFCs continue going up into the stratosphere, where it interacts with ozone, and that's how we end up with ozone destruction. Right. So how ozone is depleted. As we just saw, UV radiation produces ozone at low latitudes. I really think it means altitudes. I could be wrong, but I really think it wants altitudes. The ozone then migrates to higher altitudes. The CFC carry halogens into the stratosphere, and then they're broken down by UV, releasing the chlorine that we saw, resulting in ozone depletion when the chlorine that was released interacts with the ozone. Here is another picture of our ozone hole. The ozone hole in this picture is nearly 3 times the size of the United States. So why is the ozone layer important? The ozone layer, as we saw a couple of slides ago, blocks UV radiation, primarily UVB, which can destroy animal tissue. It can cause things like sunburn, skin cancer, cataracts, weakening of the immune system. It also has been linked to a decline in amphibian species. Here in this corner is a chart of the electromagnetic spectrum. At long wavelengths, we have infrared, or really, really infrared. So these would be radio waves, AM and TV broadcast wavelengths, microwaves. Here's what we actually call infrared down here. There's the visible spectrum, which is outlined over here. The one thing I will caution is that the visible spectrum goes from 400 to 700 nanometers, which is not 0.4 to 0.7 meters. So there's something not correct about the scaling of this particular graph. Below the visible spectrum, we have UV, X-rays, and gamma rays. As you go from the long wavelengths to the shorter wavelengths, the energy contained in the light increases, which is why UV radiation is so bad. So here is how ozone forms. It takes 4 reactions. First, you take UV light and combine it with diatomic oxygen, and that results in 2 separate oxygen atoms. You then take the one of the free oxygens, you just created and combine it with a diatomic oxygen, that results in ozone. We can also take free oxygen and ozone and combine it to get two separate diatomic oxygens. And finally, if you hit UV light, hit ozone with UV light, you end up with a single free oxygen and the diatomic oxygens. And all these are kind of integral to getting ozone out because you need to have both the free oxygen and the diatomic oxygens. Here's another act. We have the Clean Air Act of 1990. It's Title IV. It protects stratospheric ozone. It restricts production, use, emissions, and disposal of ozone-depleting chemicals like Freon. It also regulates the servicing of refrigeration and air conditioning units because they typically used Freon or other CFC molecules. The Montreal Protocol was put in place in 1987, and it scaled back CFC production by 50% by the year 2000. In 1990, there was an amendment that completely phased out ozone-destroying chemicals by the year 2000. In 1992, there was an additional amendment to phase out the ozone-destroying chemicals by the year 1996. So, by 1996, this is what the ozone hole looked like. It was 11 million square miles. The largest ozone hole ever observed occurred on the 24th of September 2006. Here's a picture of it. So here we have schematics of the size of the ozone hole and the amount of ozone over time, going from 1979 on the top one, which is the size of the ozone hole, to the year 2010. We can see the peaks and the troughs, but it is now going down, which is good. And the amount of ozone in the atmosphere is has been fairly constant over the last bit. Oops. You can look at this website if you like, which actually gives you the numbers. So, where is the ozone hole today? Where are we today? This is actually the same website we just opened, just a different portion of it. This is what the ozone hole looked like on the 8th of November 2015. And you can choose different days to go back and look. I highly encourage you to go and look at this, this website.